So this is actually chapters 1 and 2 in the textbook. I'll have to check to see if I've got my information about that on the website, but I'm pretty sure it's there. Some teachers like to do this unit first. I'm a fan of doing it near the end because then I can talk more about the shapes of the molecules. I can talk more about polarity because we've just talked about polarity. We can talk about whether things have high melting points or boiling points because we just talked about that stuff. So I'm a fan of putting it near the end after the properties and structures or test or unit. Organic chemistry, very straightforward. You don't have to rewrite that top part. You just wrote it down. The study of compounds in which carbon is the principal element. Organic compounds contain carbon covalently bonded to other elements, primarily hydrogen. So you'll notice this involves a lot of carbons and hydrogens. But there can be other elements in there, oxygen, nitrogen. In university, I took a course on organometallic chemistry, and that's how organic molecules that contain primarily carbon and hydrogen can do some bonding with some metals. It's kind of it's a little more complicated situation because you've got to talk about the way those metals can bond in there. Yeah, so you can deal with other elements as well, but we're just introducing it. Not all carbon compounds are considered to be organic. So the very simple ones like carbon monoxide and carbon dioxide and carbonate and bicarbonate and cyanide, they're not considered organic. We're talking about large groups of carbons bonded together, not just these single carbons. Historically, organic chemistry, the term organic is the same way that they use organic today to describe produce and things like that, you know, being very pure or coming from nature, that type of thing. That's the way organic chemistry was first believed. And that's why they use organic, the word organic. And that's because, again, organic chemistry is not my specialty. So I will be tripping over more words during this than in the past. Historically, chemists believed that only living things could produce organic chemicals. So if you wanted to get some organic chemicals, you had to take a plant and crush it up and somehow remove some chemicals, maybe with dissolving it with some alcohol or some type of thing, and then purify it, and then you've got an organic chemical. Or it comes from a living thing, like an animal or a human being or whatever. And they truly believed that there was some kind of special essence that was kind of endowed on the chemicals because they came from living things. There was even a term that they used in their reporting. They used to call it the vital force, with vital meaning, you know, vitality, living. And they truly believed that living things were special and that it was only living things that could produce organic chemicals. There was an experiment done, and I don't know the date, and I think I know the name of the guy. I think it was a German guy, Friedrich Wöhler. But at one point in time, he mixed a bunch of inorganic chemicals, things that didn't come from living things, and put them in a reaction vessel and heated this reaction vessel, got it to really boil and do its thing. And I think there was even an electric discharge that he was using as well. I'm not sure. And after so many days, these white crystals were formed. He wasn't trying to get those crystals. He was trying to do a different reaction. But in the end, when he analyzed those crystals, he realized that these crystals were a compound called urea. And urea is a compound that it can be removed from urine, right? Hence the term urea. And And it was believed that, well, that came from living things, and so urea is an organic chemical, but this guy created this same chemical in a reaction vessel just by boiling up a bunch of other chemicals, and that experiment is very pivotal because that told chemists that it didn't have to come from living things, that organic chemicals were not necessarily from things that were alive, they were carbon compounds, and living things are based on carbon compounds, and therefore that's why they made that confusion. They thought, okay, all these carbon compounds must be special, must be living things, but they now realize that they can create them from various other reactions. So it's not the fact that they are from living things, but it's the carbon that results in that being special. All right? Okay. Why is carbon so special? Carbon is special because it can form 4 covalent bonds. I don't need to draw the pictures on this slide. This is just, again, an information slide. Carbons can get together and they can form chains, elongated chains. They can actually wrap around and form rings. The benzene ring being an example of one, but there's many examples. We now know that they can form spheres. This particular sphere right here is actually called a buckyball, and it has 60 carbons in it, and it is a very special, stable form of carbon. Chemists for the longest time believed that carbon only came in 3 forms. Carbon that's all ground up, it's black powder, like coal, that's just carbon atoms that are kind of sitting there in a pile. Carbon in diamond, which is sp3 tetrahedral. And then carbon in graphite sheets. So there's the diamond there, there's the graphite sheets, and they believed that was it. I'm not sure the date, but we're talking 60s, I think. Chemists discovered that they were creating these little balls. They're just like soccer balls. They've got the exact same, if you look at a soccer ball where it's got pentagons and hexagons put together in little leather pieces in order to put that ball together, it's the same type orientation. They're predominantly sp2 hybridized. They're supposed to be flat, but they're able to bend enough around that they can bond with the edges and make a little ball instead of a flat sheet. They're called buckyballs because there was an architect called Buckminster Fuller. All right, and his first name was Buckminster. And in the 60s, he was an architect, and if you ever see those geodesic domes, you know what I'm talking about? There's one at Ontario Place, if anybody drives by Ontario Place anymore. It's in Toronto. Anyway, it's these domes. There's probably one in, I think there's, at Epcot. Is there one of these big domes at Epcot? Okay. Well, this Buckminster Fuller guy is the guy who kind of designed these domes. And they realized that the shape was one of these domes, half of one of these domes that he was designing. The technical term is a Buckminster Fullerene. They used his entire name and put "ene" on the end. I'll tell you why they used "ene" in a little later after the test, the next lesson. We now know that not only can you form graphite in multiple sheets, because graphite's a whole bunch of sheets, but you can actually create a single sheet of graphite. We call it graphene, all right? And they're finding that graphene, a single little sheet of graphite, a 2-dimensional sheet of atoms, is super conductive and super strong. And so right now there's a great push in materials science to study these thin sheets of carbon. We even now, as chemists, can put them into tubes, take a sheet of graphene, roll it into a cylinder, and stick half of a buckyball on each end. Not that they're actually doing that with little tweezers, but they're doing it with various chemical techniques. And they're calling these things nanotubes. You might have heard the term nanotubes. If you watch The Big Bang Theory, one of Sheldon's favorite t-shirts has images like this on it, and one of them is one of these kind of capsule-shaped objects with these little dots, and those little dots are carbon atoms, and that's representing a nanotube. They're finding that they've got strength. They're even finding that they can put chemicals in the little nanotube. So they can put atoms in the nanotube and shut it and have like a little capsule. They're envisioning maybe using them to deliver drugs not to just the body, but delivering drugs to a cell by having the nanotube deliver that drug in its little container. But they're also finding it to be toxic, right? Because they're carbon atoms, and they're not carbon atoms in biological molecules, but they're foreign carbon atoms. So in the body, they might not be so good. So right now, all kinds of exciting stuff. And this would be what we would call surface science, all right? When you get to the high end of chemistry in university, you can go into the like chemistry part, pharmaceutical chemistry, that, you know, a lot of that's good organic chemistry. But you can also then go the other way and talk about materials and surfaces and how, you know, thin little sheets of these atoms behave. So carbon is very, very versatile. And the reason it is because you can have all these different types of hybridization. You can have sp3, tetrahedral, sp2, planar. You can have sp, linear. So carbon is a very versatile atom, and that's why we have so many different types of compounds that it can create. Okay. So we need to be able to kind of categorize these groups of elements. So just like any other big group of things, and trust me, organic chemicals, the number of different organic chemicals that can exist is infinite. It's however you want to put the atoms together, the carbon atoms together, in whatever combination. The number of known chemicals, organic chemicals, is mind-boggling. It's I don't know the number. Could I say billions? I don't. Maybe billions might be a little high. We're into the high millions of combinations. And as chemists continue to create new chemicals, and they are, the number grows. It's actually growing faster now that more people are looking at the materials and trying to discover new properties of these types of chemicals. So we're talking about millions and millions of different chemicals that are based on carbon. There is no other atom on the periodic table that has such an honor of having so many compounds that contain them. It just doesn't exist. Carbon is the atom. Yep. I would agree. Yeah, because it can have expanded valences, et cetera, et cetera. And that makes good sense. One of my favorite Star Trek episodes has Captain Kirk going to a planet where there's this blob that is based on silicon, right? They took that idea in science fiction and extended it and said these life forms were silicon-based, and they ate rocks instead of food because the rock's full of silicon. I would agree. That makes sense on a surface. I don't have a straight-up answer for that. To be honest, I'm not an organic chemist. I'm an orbitals, electron stuff that we just did, more of a person. But I think when you get to the larger atoms, right? What's that? I think when you get to the larger atoms, all right, as you move down the periodic table and it gets larger, right, our electronegativity decreases, things get a little more spread out, bonds are a little weaker because things are a little bit further apart than being nice and closely knit together. So I'm going to give you just a very surface level answer for this. And I think as things get bigger, right, we become more metallic. You have lower electronegativity because electronegativity is going down. You don't have as much pull on the electrons, and they just must be less stable, right? They just don't hold together as well as the carbon ones do, all right? And I think that just has to do with a reactivity. That's the best I can give you on that, right? Or we would see it. We would see it more often, and we don't. We don't see that large number of compounds. Okay. Just like anything else that we have all these different compounds that we've got to keep straight, we've got to have a special way in which we categorize them. We've got to have a special way in which we name them. So we're going to be learning naming. And when we have a specific group of atoms arranged in a specific way, we call it a functional group. And that's how we classify these organic chemicals. We put them in groups based on certain ways in which they bond together. Members of the same organic family have similar physical and chemical properties, and that makes good sense because they'll have similar orientations of their elements, and that's due to their functional group. So we're going to be talking about different functional groups as we go ahead and learn about them. Here are some examples of some functional groups. So, the presence of a double bond. That's a distinguishing feature in an organic chemical. And therefore, we say it's a functional group. Functional meaning it provides the way it behaves, its function, the way it exhibits properties. A triple bond would be a functional group. If we have atoms that are other than carbon in the structure, those will be functional groups. Essentially, it's anything that isn't carbon singly bonded to other carbons or hydrogens. Like I said, if you've got a bunch of carbons and hydrogens bonded together and they're all single bonds, everything is very symmetrical, it's very nonpolar, and there's nothing distinguishing about the molecule. As soon as you add something that isn't carbon, you now have electronegativity differences, you have dipoles, you've got a distinguishing location in the molecule. If chemical reactions take place, they tend those other atoms to be literally electrostatically attracted to those differences in the carbon chain. So if there's no differences and they're all single bonded carbons, something that's kind of around it that's going to bump into it, it bumps into it, nothing exciting happens. But if we've got something like a carbon-oxygen where oxygen has a high electronegativity and it's got a little dipole moment, maybe it's got a little negative charge to it, then that thing will be attracted to it. If it's positive, it's going to be attracted to it. And there's going to be reaction possible. So functional groups are also areas of higher reactivity. They define how it's going to react. Yep. These molecules?
No, like biological molecules, I think like biological things.
That's what they thought. That's where you just came in. We thought at one point that it was only biological things that could create organic chemicals, but we now know we can synthesize them. We can make them in the lab.
Yeah, but like say if it's like you wouldn't be able to do like, but if you tested it like what your body's all made up of, you'd be like mostly tested.
Yes.
Yeah.
Yep. Yep. We can also have double bonds to other atoms as well as a functional group other than just carbon. Okay. Let's now talk about the simplest family of organic chemicals. And they're called hydrocarbons. And so that's where we're going to start. Next couple of days, it's going to be introducing you to hydrocarbons. and then we'll look at the different ways in which we can deal with just hydrogen and carbon. So we're just dealing with hydrogen and carbon. And then after we've got that taken care of and covered and know how to name and all that good stuff, know the reactions, we'll then move on and we'll add some other atoms into the structure like oxygen. So for now, we're talking just hydrocarbons. And therefore, they only contain carbon and hydrogen. That is not a groundbreaking statement there. So this little flow chart here is a breakdown, and you don't need to put it in boxes. That was just the easiest way to create the flow chart. This is a breakdown of the way we name hydrocarbons. So essentially, hydrocarbons can be broken down into two subgroups. Those two subgroups are called aliphatic hydrocarbons and aromatic hydrocarbons. And I have no idea where the term aliphatic comes from. I can't even begin to tell you the origin. Aliphatic, the origin of aliphatic? That'd be exciting. Yep. Yep. Aromatic. Yeah, aromatic we associate with something that has aroma, right? If you've ever seen, or if you've ever worked with benzene, which you haven't because it is a suspected carcinogen, so they've removed it from all high schools. I worked with it in university a little bit. It does have a very distinct odor. Yep. Yeah, carcinogenic is, yes, as in causing cancer, yeah. Yeah. It's not one of the bad ones. We had to do a lab that had one of the bad ones, and it was, you worked with it. Yeah. Very rarely do they have you do that, even in university anymore. So let's look at aliphatic. Aliphatic are essentially chains and rings, but they're not the benzene ring, all right? The benzene ring, keep in mind, looks like this. We've already drawn it a couple of times, right? And this is that type of notation that I introduced you to. All of the edges represent carbons, and they've got alternating double bonds, all right? And the other way in which we wrote it was, again, that hexagon, and instead of drawing it as a resonance structure, we put a circle on the inside to represent the fact that that pi bond is spread all over those carbons. It's like the smallest little piece of graphite that you could imagine. That's benzene. Aliphatics are essentially either chains of carbons or rings of carbons, but not this special ring shape that has alternating double bonds. It's the alternating double bonds that makes it special. So let's start today by looking at the alkanes, the simplest of the simple. Again, the boxes aren't special. They're just the easiest way that I could draw it on the computer. We're getting our flow chart done there. Okay, so now let's talk then about alkanes. No, I'm going to do this on the computer. We'll give it a shot. Alkanes are the only group of hydrocarbons that essentially has no functional group. It's all carbons singly bonded to other carbons or hydrogen. They're all sp3 hybridized. They're highly symmetrical. They're not exciting. But we've got to start with the easiest. We've got to start with the least exciting. Alkanes are what we call saturated hydrocarbons. It's because they don't contain any double bonds, and when something has no double bonds, it means it can be filled right full of hydrogens. So when we say that a hydrocarbon is saturated, we mean that it's saturated with hydrogens. It has as many hydrogens bonded to it as possible. The next class I teach organic chemistry, we're going to be looking at something that has double bonds, the alkenes, and we say that they're unsaturated because you could break that double bond and add a couple more hydrogens. So when they talk about things like saturated fats, a fat is a particular type of functional group. It's a special group of atoms on the end. And when they say that the fat is saturated, they mean that the chain of the fat is full of hydrogens. It means it contains no double bonds. You can't put any more hydrogens on it. It's saturated with hydrogen. Many people, when they hear the term saturated fat, think of like a sponge dripping in fat. And they say, ooh, that's gross. Saturated fat, that's gross. But people have no idea that the term saturation has nothing to do with a lot of fat or filled with fat. It has to do with the carbon chain on the fat molecule being full of hydrogen. That's what a saturated fat is. I have no idea. That'd be a biology thing. Which is the bad one? Oh my goodness gracious. I heard you say saturated, so we'll go with saturated being bad. Okay. Well, they're unreactive. We're going to learn that alkanes don't have a lot of reaction because there's no functional group. The functional group is where, and we now talk about attacking molecules. They're not really attacking, but you know what I mean. They give them a spot to kind of react with. Alkanes, they're saturated, they're not exciting, they don't have very many reactions. We name them by ending them with ane, and so now we've got to learn the prefixes in order to name these things. We use a prefix to designate how many carbons there are in a chain. So this is our introduction to naming. Yeah, if you've done the grade 12 biology, we're essentially doing that unit that you did in like a week, right? Jam down your throat, and we'll slow it down a little bit. That's why many people say take the chemistry before you take the biology. And that's why they also put this unit first, because I'm quite sure a person who is biology chemistry trained set up the curriculum and thought, oh, we'll put the organic chemistry first for all those biology students. And I'm chemistry physics trained, and I say, let's put the calculations first so we can hammer them with some calculations, give them some work to do. That's just my preference. So yes, if you've taken the biology, you know that one carbon atom will start with meth, two carbon atoms will start with F, and the ending is ane in this case, so I'll have something called methane and ethane and propane and butane and pentane, and actually after 5 it makes some pretty good sense. Pentane, pentagon, hex, 6, hept, 7, oct, 8, non, 9. Before that, it doesn't make sense. You've got to memorize the first 4, right? I always, as a student, got the F and the meth mixed up because I always thought it made good sense for the simpler one, F, to be before the more complicated one. I always got it backwards. I had a student last semester say, oh, no, this is easy. Meth is best. It's first. I'm like, what? That's crazy. But of course, everybody could now remember it, even though that's the dumbest, craziest statement in the world. Meth is first. Meth is number 1. Who would say that? But it is, in terms of naming, meth is number 1. Yeah. There's one carbon in methane. Now, methamphetamine, all right, is a big molecule, but it must have one somewhere, one something somewhere. Yeah, and I don't know what it'd be one carbon. It would be one carbon. It'd be methyl. It's a shortened form. Even methamphetamine is a shortened form, right? No. That's what everybody says. This Sanders, you should be like that chemist on, what is it called? Well, yeah, I've got one carbon taken care of. I'm recording all this, folks. Jeepers creepers. Let's keep going. This is for the other two that aren't here. All right, we'll fix this one up. We'll take it down soon after they're done catching up on what we're talking about. Okay, so meth F, prop is 3. Just got to kind of remember it. That doesn't say but. It eventually will have an E on the end, so we call it bute. So we've got things like butane, all right, so it gets a U sound. Pentex, hept, octanon, et cetera, et cetera. All right. Let's now go through a bunch of examples. Again, you don't need the grid. This is just me putting some spaces. All I need you to put are the headings, so number of carbon atoms, and the first one we're going to deal with is 1, because we're going to work our way through some of the naming, all right? And then structural formula, which I'm going to soon kind of forget about. I'm only going to do the first couple of them on the structural formula. It's the condensed structural formula that I'm really interested in, because that kind of squeezes everything in. By the way, the structural formula on that computer was when all the H's were hanging out there. That's a big ugly picture. And then the condensed structural formula, we kind of collapse the H's in on their C's so that we can take a look at what the molecule is. It makes more sense to think of it that way. Then the chemical formula itself, and then what we call the thing. And actually, I might even jump back and forth. If I'm talking about the simplest one, and it's got one carbon, what's this going to be called? Methane. Yeah, so this is called methane. Methane. And structural formula, carbon, hydrogen, 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 hydrogen. And you can see it's a pain to draw all these hydrogens, especially on this device. All right? I'm going to draw these things as being flat. We know that these are sp3 hybridized, and they're tetrahedral shaped, and that all of the dipoles will cancel out. We just did that in our last unit. We've got to keep those pictures in our minds. Condensed structural formula. If I collapse all these down, the structure isn't much. CH4, because I've collapsed the H's onto the C. Chemical formula, CH4. Not exciting whatsoever. Methane is the lightest of all hydrocarbons. It's what we use when we use natural gas, all right? It's what comes out of the taps when we run our Bunsen burners. If you've got natural gas going into your house and you cook with natural gas, that's what you're burning. 2, you're using methane. Ethane. Carbon, carbon. Hydrogen, hydrogen, hydrogen. You get the idea. I hope when we get going on this, you're just drawing it. You're not necessarily looking at me, because you're just adding a bunch of H's. Condensed structural formula. We want to maintain the chain structure, so we write this as a CH3 bonded to a CH3. So we can still see our 2 carbons, and we can see that they're connected with a single bond. By squeezing everything together, we get C2H6. Next, 3. What's it going to be called? Propane. That's the stuff you use in your barbecue. Propane. All right? Ethane is also found in natural gas. Actually, natural gas is a mixture of the two. Propane, because we're getting longer and more carbons, the London forces are greater. They're a little more stickier. Propane is a gas, but if you squeeze it hard enough, you can get it to be a liquid in a tank. So it's actually a liquid in the tank, and then as it comes out into the atmosphere, it expands and becomes a gas as it comes out into your barbecue. So as you can see here, yeah, sorry, you can go to the bathroom and grab something, or you can just use a paper towel. CCC, expanded structural formula, what a pain. We got to put in all these H's. Why do they? The convenience of the propane is that it can easily be put in a tank as a liquid. That makes it portable. You can put natural gas in a tank, but because its London forces are very weak, you need high pressure, super high pressure, so you need a super thick tank, which isn't practical for propane, like barbecuing around your house. It's convenience. Question, Joe?
I was just wondering, would that be what the difference between octane and heptane is when you got the gasoline at too high heptane, you get that base in your
That's a good question. Is it because it's more volatile because it's lighter? You're talking about knocking, like a pre-ignition situation? Yeah, it's not as good of a mixture. I'm not exactly sure if that's the exact reason or not. I really have no idea. But you're right in that different qualities of gases will have different vaporization temperatures, and therefore they could behave differently in an engine. But I'm not sure if that's the exact reason.
100%
octane, yeah. Yeah, and so as soon as you've got a mixture in there, it's going to change their properties. But I'm not 100% sure if that causes that problem that you're describing. Yeah. Okay. Notice I've collapsed them down for the condensed structural formula. We can see that there's 3 C's, and we can put our chemical formula C3H. How many are on there? 8. Notice every time I add a carbon, what's happening to the number of H's? I'm going up by 2 because now notice I'm adding a CH2 group in the middle, because every time I'm adding it to the middle, it's got to go into that chain and it expands it out. Okay, I have more on the next page. So 4. We're not going to 10. We're not going to 10. Just relax. Sheesh. I'm not doing the structural formula anymore. We get the idea. Lots of H's. Condensed structural formula. CH3, CH2, CH2, CH3. Formula, C4, H10. Excellent. What's this called? Yeah, it's called butane. Now, we're come to an interesting point. This actually is called N-butane. And it stands for normal butane. No, this one is the only one at this point. What I'm trying to say is that I could have added this third carbon. Instead of on the end of the chain, I could have actually added it to this carbon up here to produce this situation. C, 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 all right? And then my last C up top. Now I'm going to add my H's in. When I draw structural formulas, condensed structural formulas, for different molecules, and I'm not sure what shape I want to draw it, I leave the H's off. And then when I'm done my shape, I add enough H's in to give the carbon 4 bonds. So let's take a look at this carbon. How many bonds does it have right now? So how many H's will it have? Okay, very good. Excellent. 3. So now I stick in a little H3. How many bonds does this carbon have? So how many H's will it need in order to get filled? Just 1. And I'm glad you're getting impatient with me because it means that it's pretty obvious, and that's an important thing. I've had some students struggle with this. How many H's is this guy going to get? 3. And this guy? 3. All right. So what's the formula of this thing? C, how many C's? 4. It's going to be the same thing. Very nice. What we've encountered is an example of what is called a structural isomer. All right? I've got a definition for isomers on the next page, but isomers are when you have 2 molecules that have the same chemical formula but different structural formulas. They are actually different chemicals. We cannot consider them to be the same thing. They will have different melting points and different boiling points. They will combust at different temperatures. They will behave differently. And connection is everything in terms of organic chemicals. The different connection produces a different chemical. Now I've got to introduce to you a new naming system. So we're getting to the point where we're going to be ready to name some more complicated ones. This particular molecule, and the way we name more complex molecule, is we first name the chain that we have, the longest chain, and this is a propane chain. It's got 3 in its longest chain. And then it's got this branch up here. Now this branch is made up of 1 carbon. You might think it's called a methane branch. But as soon as you put it as a branch, you don't call it methane anymore. You call it methyl. So a group that has a carbon and 3 hydrogens with 1 bond as a branch is called a methyl group. We're going to write all this stuff down in a moment. Actually, I've got a sheet that I'm going to hand out that has the rules on it, and we'll write it down in a second. So this is a methyl group that's attached to a propane. So this is called methyl YL propane. Methyl propane. That's fun. All right? Now, I'm ready to talk about 5, and I don't think I have enough spaces to write it because my next page has general formula. So I might have to erase this number 4. I'm actually going to erase this right now. Everybody got that information about methylpropane? So we've got 2 isomers of butane, N-butane and methylpropane. Now I'm going to erase this page. What's that? They're both butanes. They're both examples of butane. So just to say butane would cause a chemist to go, okay, oh, the only thing I know is there's 4 carbons and 10 hydrogens. Which one are you talking about? So you got to either call it N-butane, and you can't just call it the other butane. N-butane and the other butane. I don't think that would be a good naming system. So we name it based on chains and connections. When we say propane, you know how to draw 3. When we say it's a methyl, we know we have to put 1 in the middle. I couldn't put it on the end. Let me just show you one thing. Hold on. Quit asking. I can't just put it on the end. There's too many what-ifs right now. Hold off on the what-ifs. If I were to put the methyl right there, let's say I were to put that right there, and that becomes a 2, and that becomes a 2. It would still be C4H10. You're right, then it's N-butane. The reason this is still N-butane is because all of these bonds can rotate. This molecule, in reality, if you could see an N-butane right in front of you, it's got all kinds of kinetic energy in it. Because it's got temperature and it's warm, it's wiggling and jiggling. You can think of the bonds like being little elastic bands. Imagine trying to connect a bunch of eggs, I don't know why I said eggs, to elastic bands or springs, right? It would, it would just kind of wiggle and move all over the place, right? And then if you could do that in outer space, like imagine that Chris Hadfield's doing this, so there's no gravity. And then you let this chain of 4 eggs connected by some springs or elastic bands, you just let it go. We could all imagine, because we saw some videos of Chris Hadfield, we could all imagine that it would go, right? It would just kind of wiggle and jiggle and move around. So whether I put that carbon on my picture as a straight line, or I put it up, it doesn't matter. As soon as I let it go, it's going to do that wiggling and jiggling, and it could rotate and think, okay, elastic bands can't rotate, but single bonds can rotate. Sigma bonds can rotate. So whether I draw it up or whether I draw it to the side, it makes no difference. That's still N-butane. Again, they're trying to derail my recording. They're killing me here. Crazy stuff here. All right? So if I put it on the end, it's no good. All right. Let's get rid of all this stuff. Oh, I'm ignoring Bailey today. It's Bailey. It's Rebel Bailey. She came in late. She's usually here at like 7 o'clock in the morning. And Bailey came in late today and is just looking to cause some trouble. All right. Again, I'm ignoring. So now I've got a lot of carbons to deal with. Like I said, I'm going to just go carbon, bond, carbon, bond, carbon, bond, carbon, bond, carbon. All right? And I've spilled into the other one, but that's okay. And that's because I'm going to be drawing all of these different isomers, all these different types of orientations. So once I'm pleased with this, 1, 2, 3, 4, 5, I can add my H's. How many go on the first one? H3, next, H2, 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 and H3. Excellent. And the formula, C5, H12. Actually, we can always get the number of H's for an alkane based on the number of carbons. How do we get it? What's the thing that's connecting all these things? What do I mathematically have to do with my 5? What's that? Double, multiply by 2, add 2. That's the general formula. We'll write that down in a moment. This, by the way, is called N-pentane. N-pentane. N means normal. It simply means a chain. All right, let's now draw the other isomers. I think there's more than 3, so I might need a little extra room here. My plan when I draw isomers is to draw the chain, 1, 2, 3, 4. Now, I'm taking one of the carbons off of the end, and I'm asking myself, can I put it somewhere in the chain to make a different molecule? I've already said, if I put it on the end, what do I recreate? N. So no good. I put it on here. Exciting. Frustration is growing. So I put it on this one. Excellent. H3, this guy up here, H3. Down here, H3. Oops, that's an H2 in there. Oh, no, that's just an H. Woo! I'm flustered now because of all the criticism that's going on today. H2, H3. Excellent. Again, C5H12. We're not surprised at that. What's this called? Methyl. Butane, that's fun. Methylbutane, excellent. Now my next strategy would be to take this methyl group and move it on to the next carbon. But that's the same thing. If I flip that over, you'll notice I'll just have the same molecule except it's flipped over. And that is the same molecule, so that's not something new. So taking this guy, putting it here, I'm going to get the same thing. If I take this guy and put it on the end, I get the N-pentane back. So I'm kind of done moving around that particular methyl group. But I could take another methyl group off of the chain and stick it into the middle one and get kind of like a T, right? So there is only 3 on this one. I wasn't sure. So C, C, C. There's my propane chain. And now I'll put a methyl group there, and I'll put a methyl group there. And that is H3. No H's on the center guy. H3, H3, H3. Again, it's C5H12. It is the same formula, but different structure. And now I have 2 methyls. So I have to use some other prefixes in order to do this. What's that? No, I don't use an ethyl. An ethyl would be made up of a chain made up of 2 carbons, not 2 1-carbon chains. Okay? This is actually called dimethyl. Dimethyl to represent 2 methyls. And what's the chain that I stuck this to? No, it's not a butane anymore. It's a propane, because there's only 3 in my chain. You could look at it as a chain up and down with 2 up the side, makes no difference. It's a propane. Propane. I apologize for squeezing that into the bottom. And that's the end of the isomers for pentane. You can imagine as we go to higher and higher numbers of carbons, we get more and more possible situations for isomers. Let's stop there and write down the general formula. Yep.
like chain,
Yep.
and you stuck a methyl on, like, if you stuck one here,
Yep.
one here, one here, one here, would that be?
That would be tetramethyl
Okay,
tetramethylbutane.
It's still a methyl.
Yes, even though you've got a bunch of methyls. Yep. And we're going to go into more complicated ones, and by the looks of it, it's going to be on our next lesson just by looking at the time. So, CnH2n, I think we saw that trend. So if I was talking, and then again, I'll just give you an example. So we could simply say, what if we had C60? Because we could simply have a big long one. We're not going to name it, but how many H's would there be? 122, right, would be the formula. So next I want to define structural isomers, because I just talked about it. So structural isomers. What's that? Oh my goodness gracious. Normally I don't teach about geometric and optical, but because you're so keen on it, I may bring up geometric and optical. I was looking at some old chemistry stuff from a curriculum back in 1988 last night, just to compare what I do now. And we did talk about geometric isomers, and I might just to discuss it. Goodness gracious, you guys are whiny today. Is this the pre-prom wine fest? Is that what this is? Really, before you came, Bailey, I thought for sure we had the pre-prom something going on. Some hair something, maybe some nail business or... Structural isomers of a hydrocarbon have the same chemical formula but a different arrangement of carbon atoms. The easy way to determine whether you've got structural isomers is to name them, and if the names are different, you will have two different molecules. The naming system has been created so that isomers cannot have the same name, so they're not confused. That's the way the naming system was designed. It is chemistry, so it makes good sense. I can actually get started on the naming. We'll see. I might actually just get to this sheet. This is going to work out okay. I used to have everybody write down all the rules and draw all the molecules, and it was a very slow process. But I can now do this a little quicker. One last little slide here that finishes this particular lesson before I go on to this handout. Nothing to write here except one little piece of homework, but we can just leave it aside for now. Don't write this down, but this just indicates how the number of isomers grows when you have more and more carbons in a chain. So you'll notice CH4 was 1, and ethane was 1, and propane was 1, and butane was 4, and pentane was 3. But as soon as you get to 6, there's 5 of them. 7, there's 9, 8, there's 18 different isomers, and if we had something like C40H82, that's how many different isomers you could draw. And the homework I was going to ask you to do is draw the 9 isomers of heptane. All right, so write that down as homework under your structural isomers. Draw the 9 isomers of heptane, the 9 different structures that you can have with 7 carbons. Oh, come on. Goodness gracious. Yeah, that's part of your homework. Not really. It's 9 structures. All you got to do is come up with 9 different connections. I might, but I might not. That's what might stands for. You don't have to write all this stuff down. Just write down Draw and name the 9 isomers of heptane. There's 9. I'm telling you there's 9, so you don't sit there and draw all day long and you have repeaters. Okay, now I do want to go on and talk about how to name some more complicated ones. So I'm going to switch over to the Word document, which is exactly the same document that you have right there. And the way we name it, and I kind of gave you a little informal lesson on how we name these things. But one of the most important things was that main chain, the parent chain. So rule number 1 here, we've got here, identify, can I write on this thing? Yeah, I can. Identify the parent chain. The chain might not be a straight line, so you got to watch for it. If it's a cyclic hydrocarbon, because we can make them into some rings, then the number of carbons that forms the rings becomes the base name or the main name. And we put a prefix of cyclo in front of it. So we can have something like a cyclohexane. That would be a ring of 6. All right? Cyclo means it's in a ring. If we don't put cyclo on it, it's not a ring, it's a straight chain. Number the carbons along the parent chain, beginning at the end, that will result in the lowest numbers for the branches. We haven't had to number our branches yet, but we will be numbering the branches. It's like we're going to give the branches a little address so that you know where to put them. If it's a ring structure, the parent will always start at a branch. I'll go over these as examples. They make more sense as we go with examples. Name each branch and give it a position number. Write the branches in alphabetical order. Whenever you're writing a list of branches, always put alphabetical order when writing that list of branches. So alphabetical order comes into play quite a bit. If the same branch appears more than once, the quantity of the identical branches will be given a prefix like di, tri, tetra, penta. So we don't use meth-eth, but to count like 2 branches, we say it's dimethyl or diethyl or trimethyl. All right? If the same branch, we talked about that. Put everything together. Then you put a number, then the branch, and the number, and the branch, and the parent name, et cetera, et cetera. Let's just do some examples, and I'll show you what we're talking about here. I don't want a line there. I want to move this thing down. Okay. And now I'm going to zoom into our first picture here. See if I can do this. Zoom into the first picture. I want to go zoom in a little more. There we are right there. Okay. Let's take a look at this first one. Yep. Oh, you've got an alkyne page. How did that get mixed in there? Alkyne, and you didn't get any page? Oh, so you got that. That's my master page. Actually, I'm going to switch yours around. You ended up getting my good copy. That's what I started with. See, that's a photocopy page. That's my master page. That's what happened there. All right. Are we good? Everybody got a page? Okay. Here's the way we're going to do this. We need to find the longest chain. It's the longest continuous chain of carbons. 1, 2, 3, 4, 5, 6. See how I can get 6 from there? I might think this is my chain. 1, 2, 3, 4, 5. But that's not as long as the longest chain. I always want the longest chain. So it looks like our parent chain is 5. I need to number, 6. Looks like our parent chain is 6. You know the way I get when I get to the end of the class. I'm screwing everything up. I just want to give you a heads up on how to do this. I number because I want to give our branch an address. And I always number such that the branch gets the lowest number. So if I number from this side, 1, 2, 3, 4 is where my branch is. But if I number from this side, 1, 2, 3 is my branch. So I'm going to number this chain 1, 2, 3, 4, 5, 6. Now I'm going to name my branch. I'm going to change colors here, but there's no need for you to do that. There's my branch. And it's a CH3 branch. So what is this called as a group? We just used it. It's a methyl instead of a methane. All right? So this is methyl. So I always do my naming in reverse because I like to write the parent name first, but that's the last part of the name. So I write down at the end here, hexane. That's the base name. It comes from my chain. And now I'm going to write my branch. This is a methyl in the number 3 position. So this is a 3- methyl hexane. There's no space when you put two words together like methyl and hexane. If I want to separate a number from a word, I use a dash. Okay? Let's take a look at this one here. Actually, we've already seen this one. This was the example we just did a moment ago. Yeah, here we've got a chain of 1, 2, and 3, and I've got a methyl group and a methyl group. You might think this should be called 2-dimethylpropane, but there's nowhere else to put the methyl groups. If I put the methyl group on the end, I turn it into a butyl chain. I make the chain longer. When the numbers aren't needed, because there's only one place to put them, we don't put the numbers. You only put the numbers when you need to put them. This guy, I had to put a number because I could put it in the number 2 position, and it would be a different molecule. So I need to put the number when it differentiates for a molecule. This is just called dimethylpropane. Oh my goodness. I wanted to slide over here. Oh, and my writing stays. Terrible. I would like to do one more example, but we're right on top of a bell. I would like to get rid of this. Yeah, they get a little hairy. We'll do more of these later on. I just wanted to tell you right now quickly, this group right here has 2 carbons in it, and it's a branch. What do you think it's called? Yep, it's an ethyl branch. Ethyl. And this has 1, 2, 3, 4, 5, 6, 7, right? And it's on the number 3 position. This is a 3-ethyl. It's on the number 4 position. As time gets closer to the end, you know the way it works. It's the number 4 position. 4-ethyl, and what's the 7 guy going to be called? Heptane. I am going to do more examples on Wednesday after the test, but you can at least try to name your heptane isomers. You can now name your heptane isomers. If you really want, you can try some of the naming that's in the homework as well if you want to get ahead. Yep. Right, so you're going to have, it would go, you would put ethyl first because it's alphabetically first, and then the methyl, and you would give notice they're both on the number 3 position, right? You'd give the ethyl the lowest number because it's alphabetically first. So you'd have a 3-ethyl, 4, 5, 6, 7, 7-methyl, 8, 9, nonane, 3-ethyl, 7-methyl nonane. That was a quick rush. I'll review that when we get back, okay? Or when we're done the test.